Hi guys, welcome back. In today's video, we'll be talking about derivatives. Now, what is a derivative? We'll get to that. Now, this is like really the first part of calculus, right? We covered limits, some parts of limits, in the last couple of videos, but really, limits are the middle child. Nobody cares about them. Like, everybody forgets them, but not a derivative. Derivatives are the youngest child. Everybody wants to spoil the youngest child. Now, the oldest child will leave for a later one, but his name starts with an I and ends with integral. Oh, shoot. Let's get to derivatives. By the end of this video, you'll be able to do three things. One, you can explain what a derivative is. Two, you can get a general equation for a derivative based on some particular function. And three, you can find the derivative of a function at a particular point. Now, let's get to number one. Here is the definition of a derivative. Given y equals f of x, the derivative of f of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. What did I just say? Don't worry about this. Don't worry about this. This is just fancy math work. I think what's better is that I show you some visual representation so you can better understand what this actually means. So let's get to that. Take this graph, for example. Okay, this is some random f of x graph. What you'll first notice that it's curved. It has a curve. And actually, I should do this in another form. Okay, now the yellow function is f of x. So we start at a base point, x. Okay, now what we'll do is that we'll go over some distance. Let's call it h. Okay, it's just a tiny distance to the right or to the left, does not matter. Now the resulting x value is x plus h. Now on the y-axis, the value here would be represented as f of x, and this one would be represented as f of x plus h. Okay, we clear on that? Great. Now what a derivative is that it's basically rate of change at a single point. Now that sounds weird. Change implies that there's at least 2 points of reference to actually see any difference in. But how am I supposed to figure out change if you just give me 1 point? So we're first going to draw something called a secant line, which just connects these 2 points. Now, the next thing we do is that we are going to shorten this distance. We're going to make h, the distance from here to here, we're going to make it super small. Incomparably small, so small that it's just insignificant at that point. Now you see here that the distance has shortened. H has become a bit smaller compared to the last graph. Now we can draw another secant line. Okay, it's getting a bit smaller now. It's getting towards a point. Okay, so then how about we do H even smaller now? Now, there's only so much space I can represent here, but you get the idea. We're making H really, really, really small. Just small to the point that if I have another graph, that at some point, it'll just be just one single point. It'll look like a single point. And from there, we can take the slope of the resulting secant line, which is technically now a tangent line. Because remember, change, you need 2 pieces of it. You need 2 reference points to actually take a look at what's changing. You can't realize change just from one single point. So really, if you were to zoom in on this, like zoom in more and more and more and more, like as much as you can, in reality, there'd be 2 points here. But in the grand scheme of things, like h, that distance that separates the 2 points, are just so small that at that point, it's just a good enough approximation of what the tangent line slopes would be. Another way you can think about this. Take a look at this box that represents x squared. Now, some of you may recognize this from Grant Sanderson's videos on essence of calculus, and I really like his explanation, so I'm just using that in my video. But basically, the idea behind this is that we have a square that is labeled as x squared, the area. And it, of course, has sides x length and another x length. Now, what the idea is that what we're going to do is we're going to make this box just a tiny bit bigger by h, a little bit h more, okay? So then, with that, we get a little bit of that, a little bit of this, and a little bit of that, we have now a bigger square that can be divided into 3 different pieces. Now, I'll label what they actually mean. Okay, you see these 1, 2, 3, 4, 5, 6 labels I put on here. These basically represent what the lengths are of this rectangle, and this little square that's been made. So now we can take a look at what they actually represent. So the new area, which I'll say is NA, new area, okay, that'll be equal to h times x plus h times x plus h squared. Okay, we can take a look at this. We can confirm this because look, h times x is that area of this square, the rectangle. H times h is this h squared, and then x times h is just another one, same as this. We can combine these two, right? So then we get equals 2hx plus h squared. Now what you'll notice is that both of these have h's in them. And remember, the idea is that h is a really, really, really small value. And h is, in calculus terms, h would represent a dx, okay? So really what this is that if we had the original function x squared, right, x squared, the new area would be this divided by h. So this will get out, this will get out. So then we'll just have 2x plus h. But remember, we want this h, we want these h's to get really, really, really small. So small that it's basically insignificant. Okay? So in the end, when these are out, now we're not dividing by 0 yet. I want you to know that we're not dividing by 0. H is just getting really, really small. We're taking a limit. We don't care what actually happens when h is equal to 0. We care what happens as h approaches 0, which in this case just goes to nothing. So you get 2x. What this 2x means is that the rate at which the square is growing in proportion to a little bit more h, we can signify with this function. I know that sounds complicated. I think a better way to understand this would be by showing you a graph. But now we're going to look at the formal definition of what a derivative is and see how we can get this by rigorous mathematics. Okay, so going back to the original function we had, f of x equals x squared, we're going to use this formal definition of a derivative to figure out what the derivative of x squared is. And we already found it out from last time that it's 2x. Now we're actually going to prove that, okay? So you see this right here is how you signify that we're taking the derivative of a function. Now, this can be many things, okay? This can be f with this apostrophe of x. If it's like y equals x or something, that'll be just a y, like that. Or it might even be something like df dx, which is the more, man, who did it? I think it was either Newton or Leibniz that made it like this. I think it was Leibniz that made it. Leibniz was one of the founders of calculus, but I just want to tell you that there's different ways that you might see the representation of a derivative. But for our purposes, we're just going to use f prime of x, I think that's how you say it, or just the apostrophe. Now, we know the function to be x squared, so we get limit as h approaches 0 of x plus h squared minus x squared over h. Okay, now you always have to bring down the limit because we are taking the limit. So that equals the limit as h approaches 0. I know my handwriting's bad, but this is going to be h squared plus 2xh plus h squared minus x squared. Now look, this right here looks very similar to what we saw on the square representation. And this is all going to be divided by h. Now look, this cancels out, that cancels out because they're subtracting each other, okay? So now we have equals the limit as h approaches 0 of 2xh plus h squared over h. Okay, you can factor out an h, so then h, and we just have one h left. So then from there, we get the limit as h approaches 0 of 2x plus h. Now we can just do a direct substitution, and we get 2x. Boom. Isn't that amazing? Now, what I do want to say is that this was a very, very easy problem. If you really want to improve your algebra, okay, this might seem very strenuous, very rigorous, something that you might not want to do. But what I just showed you is something called first principles. Okay, it's basically how you take the derivatives, the first principle of calculus. If you want to improve your algebra skills, I'd recommend that you do this with different functions, because later on we'll be covering shortcuts. Like x squared, you can take the derivative of that without doing all this. Just looking at it, you'll be like, oh yeah, it's 2x, easy. Not just for x squared, for anything, because there's shortcuts for this that we found out. But if you really want to improve your algebra, do this. I know it's long, especially for ones like, I don't know, f of x equals cosine x ln of x. Like, what? Like, who's going to take the derivative of that using just that method? I'm like, it's going to take so long. But really, if you figure it out, algebra skills are on another level, man. Okay, now we've already done 1 and 2, the two goals, right? We've explained what a derivative is, and I showed you how you can get the general equation for a derivative. Now we're going to be covering how do we get the derivative at a single point. And really, it's simple. It's just plug and chug. So let's say I ask you, given the function f of x equals x squared, what is the rate of change at x equals, I don't know, 10? Okay, 10 for example. So let's say that's 0 and this is 10. Okay, so it's just a simple plug and chug where we do not put it into the original function, we put it into the derivative function. If we put it into the original function, then we're just getting an output, a y value, which is on this. We don't want that. We want to know the rate of change at x equals 10. So f of 10 equals 2 times 10, which equals 20. What does 20 mean in terms of this problem? If this right here is the point f of 10, then if we draw a line tangent to it like this, okay, a line tangent to it, this 20 represents the slope of this tangent line. That's what it's saying. It's really clever how the founding fathers of calculus were like, okay, we can't really take one point and figure out the change at one point. We can't do that. But instead, how about we take a tangent line and figure out the slope of that? We can figure out the slope of a tangent line. Okay, in terms of x squared, that's a curve. Any curves, I'm done. I don't know how to calculate the slope of that. But if I phrase it in a way that I can take the slope of a straight line, then I might be onto something. And this is what they came up with. Gottfried Leibniz, Isaac Newton, all the other founding fathers of calculus, that's what they've got up, that's what they found, and they were like, oh yeah, baby, we're onto something. So this 20 here represents the slope of this tangent line. This works with any other number. Can you imagine how strenuous it must be for one to, I don't know, take 2 points, right? 2 points on the graph, and then make them shorter, and then find the slope like that over and over again for like infinite numbers? Like, no, that's just way too much work. But look, this derivative just does it all for you in 1 second. Okay, so simple plug and chug. And then you can also find the equation of this, right? You can see like, oh, it intercepts this point, oh, it's moving, but you get the idea. Yep. All right, guys, thank you for watching today's video. That's it from me. Make sure to like, subscribe, leave a comment, please. Like and subscribe. The family business has not been going well. I pray every day. Be grateful for life. I'll see you next time. Peace.